machine learning pipeline is what we talk about today. The machine learning pipeline explains the whole process from the very beginning, like selecting data sets, pre-processing the data sets, defining your problem, then choosing algorithms, tuning your models, or training your models, tuning your models, and evaluating your results. It's very important. It's not very algorithmic. It's very practical what you learn today. After last lecture where we learned about linear regression, but before we start, we will watch a quick video. And I don't know why, I mean, you probably have realized that as well. Many videos on YouTube are in this style. It's kind of weird, I think, these faces, but it apparently makes it more likely that people watch this. It always looks like clickbait to me if I see a video like this, but this guy, Matthew Berman, he's doing very nice videos. I think I recommended him to you already in the first lectures. His channel is very easy to understand and to follow news on AI. He's a very positive person, sometimes maybe too positive. I think sometimes you should be a little bit critical, but it's pleasant to watch if you're on the train or on the bus or wherever you watch videos. So let's watch this video. It's a few days old and it's quite interesting content.
This video is brought to you by Vultr. More on them later. We now have a humanoid robot built for home use, available for pre-sale right now. This is 1X's robot, Neo, and it is really the first mass market pre-orderable humanoid robot that we've seen. And their launch video went absolutely viral, almost 30 million views in less than 24 hours. And yes, I already pre-ordered it. It's gonna be available in early 2026. That is right around the corner. Neo is offered at a $20,000 purchase price or $499 a month. Now, let's talk about that purchase price. Obviously, $20,000 is a lot of money, but relative to what it's actually going to be able to do, it's quite affordable. There are only 3 cars in the United States sold for under $20,000. So this is really on par with the cheapest cars to buy in America. It weighs 66 pounds and can lift, listen to this, 150 pounds. It has 22 degrees of hand movement and is extremely quiet, coming in at about 22 decibels. This thing hopefully will be able to do things like fold your laundry, do your dishes, organizing, tidying up, but not everybody is convinced it is going to be really great. Some initial reviews of demos that were given say that it's still teleoperated for the vast majority of use cases. And here's the thing, when it launches in 2026, if it's not able to accomplish something, somebody will be there ready to teleoperate it at any moment to complete the task. That's kind of nuts to think about. Imagine how much infrastructure, how many humans they're going to have to hire to make that happen. Plus, the whole promise of humanoid robots is to be able to be autonomous and run 24 hours a day. Congrats to 1X. I am very excited for the humanoid robot revolution. Of course, as soon as I get mine, I'm gonna test it out. I'm gonna make a video about it and I will share my thoughts. And next, Extropic has released new information about their thermodynamic computing platform, a completely new way to do compute. If you're on Twitter, you've probably heard of Based Beth Bezos. He was an anonymous account that was really popular, started the effective acceleration movement, and then it was revealed that he is actually one of the founders of Extropic. And he's been talking about what Extropic does. And to be honest, it is very difficult to understand, but I'm going to try to break it down for you. Their pitch is that current computing paradigms require far too much energy. They are completely energy inefficient, and they have been able to unlock incredible efficiencies not seen anywhere else. And they have introduced the first scalable, probabilistic hardware, inventing both new hardware and new software to run on it. It is called the Thermodynamic Sampling Unit, TSU. The TSU is very different from a normal CPU or even a GPU. Instead of executing deterministic commands, it samples from probability distributions. If that sounds confusing, that's because it definitely is. But you already have been working with non-deterministic systems. If you've ever used AI before, that is exactly how AI works. It comes up with a probability of what the next word in a sequence of words is. And so they're taking that approach and saying, well, why can't we do that with hardware? And they are claiming that the TSU can be up to 10,000 times more efficient than traditional CPUs and GPUs. Now, it's still very early. These are just prototypes and simulations, but it's exciting. Anybody who's working on something cutting edge, completely novel, you have my love. So I really hope they continue and have success with this new computing paradigm. Next, we have a new open source model, of course, from China that has broken previous intelligence records. According to artificial analysis, MiniMax's M2 achieves a new all-time high intelligence score for an open weights model and offers impressive efficiency with only 10 billion active parameters out of a 200 billion total. It is very efficient to serve, and look at this. MiniMax M2 coming in at 61 on the Artificial Analysis Intelligence Index, right below Claude 4.5 Sonnet, right above Grok 4 Fast, and of course, leading the pack, GPT-5. But it's kind of crazy to see that it is better than Gemini 2.5 Pro. This is an open source, open weights model that you can download. You could potentially even run it locally. I'll drop a link below to this benchmark. And if you want to run models like MiniMax and other open source open weights models, you should do so on the sponsor of this video, Vultr. Vultr is the world's largest independent cloud provider, and they've been a fantastic partner to us. Back to the video. All right, next, in news that I did not see coming, Nvidia took a massive stake in Nokia. You remember Nokia? They used to make phones before the iPhone came out. And to be honest, I don't really even know what they do anymore. But those phones were iconic. They were absolute beasts. They were bricks. You can drop them from a skyscraper and they would still work afterwards. And according to CNBC, Nvidia takes a $1 billion stake in Nokia, sending the 5G equipment maker shares up 22%. And listen to this, the two companies also struck a strategic partnership to work together to develop next generation 6G cellular technology. And the 5G and 6G software will run on Nvidia's chips. Nvidia maybe doesn't know what to do with all of that cash. They are buying huge stakes in different companies like OpenAI, and then OpenAI takes that cash and buys chips from Nvidia. It just seems like either the ultimate 4D chess move or potentially a Ponzi scheme. Either 14,000 people. These are all corporate jobs, not factory jobs. And it is a mass layoff aimed at readying the company for wide adoption of AI technology. Now, I have so many thoughts about this. Do we really think that they're laying off 14,000 people because of AI? I know a lot of you probably do. I personally don't. This is kind of the natural ebb and flow of company growth. They probably overhired and need to start trimming down. And of course, AI is going to allow them to leverage up each individual employee, but this is probably just more of a function of overhiring in the past and now correcting for it. Remember, for years, these companies were hiring so many people every single year, and eventually they get a little bloated and they need to trim the fat.
So those were just some of the news in the last week or so. I show this to you just to illustrate once again how much is happening in the domain of AI. I'm teaching you about a few algorithms, about a machine learning pipeline, but every week or so there's massive news like Nvidia invests again billions of dollars into other companies, or the robot that is being released. I mean, let's see if it's really being shipped in January. So the first news about Neo, this robot for your home. And I'm not sure if you are aware of how much this is possibly going to change society and how crazy this is. It's teleoperated in the beginning, at least. So people buy a robot, put it to their home, and then other people working for the company can look through the robot's cameras directly into your home and will do your dishes for you and whatever. So if you think about privacy, that's a completely new dimension. So far, people were concerned when there was a camera at the train station or something like this. Now, at least some people have cameras directly in their home. And it's really interesting to see that the robot is not autonomous in the beginning, at least not for the most part. And why is that maybe still a good idea? I mean, remember one of the first lectures I told you how difficult it is to get good training data for machine learning. And I assume this company had to decide, well, okay, we could do it like all the other companies. We invest millions or billions of dollars over years. We build some research labs, some simulations where we build a kitchen and we build a bathroom, and then we put robots inside our lab, let them do something. We will correct them. Like if they do something wrong, we will tell the robot, no, do it like this. And it will take years, and it's expensive to build such facilities where robots can train, or to write a simulation where robots can do that. So this company decided, okay, let's just put the robots into real homes. Some people will be willing to even pay $20,000, and we can collect training data kind of for free. I mean, not for free, they still have to hire, of course, the humans controlling the robot. But it's a very promising business model. It shows how important it is to have good training data, and how much some companies are willing to invest to get that training data. And I think there's a good chance that this company will not regret the way they did it.
15,000 is a lot.
So let's get back to the normal machine learning things, the machine learning pipeline. So let's look at this. This should look familiar to you. It's linear regression. You have here some data, some linear regression data on the x-axis, the variable, here the label, and a linear model. And you also say that the degree of freedom or the power is 1 because it's linear. You could have higher degrees of freedom, which make you more flexible in your model. Now, with linear regression, you always have a straight line, or like a plane, or at least a linear model. If you had, instead of x1, x2, x3, if you had x1 squared, x2 squared, something like this, you could have a quadratic model, or you could have the power of 3 or to the power of 6, and so on. So then your model could look like this, or like this. Or if you have a very high degree of freedom, let's say 15, it could look like this. So your model would fit those points much better. Which model would you choose? Which degree of freedom? Get out your phones, please. Go to menti.com. Think about it for a second. Use this code. Why? What does it depend on? Who chose this? Yeah. Okay. Any other opinion? What does it depend on, or why do some people think linear regression is best, or this one, or here. Yeah.
That accurately is ends up performing better because it's efficient, probably.
Yeah. And I would not fully agree with, well, that, let me give you my answer. I would argue it's not really possible to answer the question here. It's not really depending on what you want. If you talk about machine learning, it's always minimizing the error or maximizing the prediction accuracy. It's not possible here to exactly know which one is best in terms of, I mean, you don't see numbers, you cannot do any calculations. And most importantly, what I mentioned last time already briefly, you always must, and we talk about that in more detail now, you always must split your data into a training set and a validation set. So you always would choose some points randomly that you remove, you train your model, and then you use the model to make predictions for the removed points. Very likely, there's no guarantee, but very likely, this model would not be best. And very likely, this model also would not be best. This model very likely would be overfitting the data. You will learn in a few minutes what that's meaning. And this model would be underfitting the data. So I wouldn't know if this or this or this model is best, but probably one of those. Definitely not, or very likely not this and not this. And actually, the answer, it depends, might be right based on the question, what is this data? I mean, is it the training data or is it the test data already? If this was the test data, then this would be best. But and if this is the training data, then you wouldn't know at all. But anyway, we talk about that in much more detail. We will talk this lecture and maybe even next time, let's see, about preparing your machine learning experiment. So that includes defining the problem, which is not easy, to get and understand the data, which is also not easy, as just the example with the robots showed. It's not easy to get training data. Identify promising machine learning algorithms. And it's a circle. Yeah? And not only this is a circle, also the next step, you might go back to the first one. But then in the next step, you train and test your models. You optimize the algorithms and you pre-process the data. And that's something we will talk in this lecture a lot about, how to pre-process data. So this part. How can you clean your data set? How can you treat missing values, select the features, transform data, and many things more. There's many things you must know before you can, let's say, really productively use machine learning algorithms. It's not just enough to know the algorithms or just enough to know how to start an algorithm in your machine learning library. And then one factor that we will not cover in this lecture series, but which is not less important, is really how to deploy the model, monitoring the model, and report to stakeholders. What is a stakeholder? Yeah. Yeah. So someone who has an interest in your work. Not like someone, but like typically people in your company, your boss, your employees, your team and colleagues, possibly the media is a stakeholder. There's many ways of visualizing that. I will not ask that in the exam. I will not ask you in the exam, please draw this plot or something. You should have a basic understanding of all the things that are necessary. Yeah. So let's start with the core, the training and testing the model. In the lab sessions and here in the lecture, we normally talk about offline evaluation. You have your data set, your matrix. You train your model on the data that you have. So you have your training data, and then you build your models based on that. And the assumption is that if your model performs well on the training data, then it will also perform well on future data. And in machine learning, that's often true. You know, if you if you have images of cats and dogs and you train your machine learning model to detect them, and then you use this model with new images of cats and dogs, it very likely will work well. In some other disciplines or in very specific domains of machine learning, that's not the case. Like my primary field of research, recommender systems, it's not often the case that if something works well in an offline evaluation, that it also works well in an online evaluation or the production system. There's various reasons, but just one reason, just to give an example, let's imagine I have data from you, like about your study time and your average marks and your salaries, and I train a model on that, and I would then deploy the model in the United States to some students. It very likely would not perform too well, the model, because students in the United States are just too different, or the job market is too different. Salaries are much higher in general, and some other factors. And here in the lab sessions, of course, we just don't have access to online data. So the naive evaluation and assumption is you train your model on all your data, and then you validate it on the same data. The problem here is it will lead to overfitting. And what that means is illustrated here. Overfitting is here. So if you continue to train and train and train and train your model, always with the same data, at some point, your model will learn almost everything. It will learn almost every point that you have in your data set. But the problem is you can already expect, sorry, there's noise in your data, only because, let's look at some outlier. So the blue dotted line would represent the real model that no one knows. So if in the next step you would have a new instance here, then the real best prediction would be here on the blue dotted line. But because unfortunately in your training data, you have these few outliers here, your model is like skewed to the top, but it's not providing the best result. So what you would want to have is a model like this, the red model. Again, it's never exactly like the true model because no one knows the true model. But in practice, this would deliver the best results. So if you have very complex models with a very high degree of freedom, or some neural networks with many, many layers and neurons, they tend to overfit easily. Just another illustration. Imagine you want to classify the red crosses and the blue circles. And this is the data that you have. You probably would not want a linear model like this, but rather something like this, even if it's not perfect. Even if basically this and this point would be misclassified now. And you also don't want something like this. It's perfect on your training data, but it very likely would not perform well on new unseen data. So what you therefore have to do, you must do that. You cannot use this naive evaluation. You must use some hold-out evaluation or some other approach I'm going to show you. An hold-out evaluation has your training data, the whole 100%, and it splits your training data into, or it splits your whole data set into training data, for instance, 80%, and validation data, for instance, 20%. It can be 80-20, it can be 90-10, it can be 70-30, something like this. And then you are training your model on the training data and measuring its performance, you validate it, on the remaining 20%. And that's the result that is interesting. That's the result you are reporting to your stakeholders or that you just used to look at. And that's the one you want to optimize. You want to have the best possible result on your validation data. Just to illustrate that again, imagine this is your data, your full data set. And then you randomly choose some data points as validation data. You train your model so that it's as good as possible in the beginning on the train data. And you use the same model to measure the error on your validation data. And if this is not good, you continue here. More precisely, you continue here until your stopping criteria is met here. So if this error is 0, or if this error doesn't change anymore, or if here the error goes down and down and down, and then it goes up again, then you know, okay, I have passed the local or the global minima. And then you continue or stop training here. Here, if you would take the higher degree of freedom, for instance, the power of 4, so it's the same data, your model might look like this, or even like this, with a very high degree of freedom. And you, well, I'm not sure if you can see that, but you probably see that this is not perfect and this is not perfect. And here, this is quite perfect. Here, the distances between the model and the real data points are relatively small. Here, this distance and this distance and this distance are relatively large. And here, at least also a few data points are really far off. When you do machine learning, you will work with different curves that you are observing, or at least that are in your mind to understand. So a typical training curve looks like this. Your error should decrease and decrease and decrease and decrease on your training data, because your model just gets better and better, or with gradient descent, at least it's not getting worse. Once you have achieved your local optima, the gradient is 0 or near 0. So there is no update or almost no update of your weights. And therefore, the error stays more or less the same. So it improves and improves and improves. Then you have hyperparameters like this, where it could go up and down. Now that's looking for an optimal K. We had that in one of the last lectures also. It could go up and down and up and down, and then maybe you see here the accuracy is high. So this has nothing to do with training. When I talk about training, this refers to finding the optimal weights, for instance, for linear regression. Or this would be the degree of freedom, where in the beginning also increasing the degree of freedom would reduce your error on both the training and the validation data. But at some point, if you see this, if this is the degree of freedom and you see the curve goes up, you know this chart is on the validation data. On the training data, the error should never go up if you increase the degree of freedom. If you increase the degree of freedom, the error on your training data will go down normally. We also say that once the error does not change anymore, that your training has converged. That's an important term. You should just remember it. If your training has converged, it means, well, you are done, basically. So what you can expect if you have your training data and your validation data, just once again, your training data probably goes down and down and down, and then it's stable maybe, or it even goes down further. But if you then compare or apply your model on your validation data, there will be a point where the error goes up. And that's the point you want to find. That's the model that you want to use in your production system. You can see the validation data as a sample of the new unseen data that you will occur in your production system that you don't have, but it's the best approximation of that. So for the evaluation, the validation error is much more important than the training error. It doesn't really matter what the training error is. As an extension, you could use k-fold cross-validation. K-fold cross-validation means that you are splitting your data set, not just into training and validation set, but you do this k times. You split your data into k folds, 5 or 7 or 10 folds. Use k minus 1 folds, so let's say 4 folds for the training and 1 fold for the validation. After that, you use some other 4 folds for the training and another remaining fold for the validation. So you do this 5 times. So you do your training 1 time with this and evaluate it 1 time on this fold. You do your training another time with this data and evaluate it on this fold. And you do it and so on and so forth. And you do your training on this data and your evaluation on the last fold. And then you are averaging your results. And that is what you then, the result you report. It makes sense, especially for small data sets, because this approach ensures that every data point is at least used once for training and for validation. On the next slide, you see, and I think I have that chart. Did I show that to you before? Yeah, I think I showed that to you before. So just a reminder how strong results in machine learning can vary, especially with small data sets. You see here, they try to find out the optimal k, but it doesn't really matter what they tried out to find here. So you see that for every time that they run this 5 times, well, you don't see it here, but here, 1, 2, 3, 4, 5. And every point represents basically the result of a normal holdout split, let's say an 80-20 split. Only that this time they used cross-fold validation, so they did this 5 times with different splits. And you see that the results vary quite notably. So if you were to do only a normal holdout split, it could be that you either get this result or this result, or this result, or this result. Building the average gives you a much smoother error curve and therefore allows you much better to determine which k to use or where to stop the training. So yeah, here I plotted the holdout error, or the validation, the k-fold validation error always as lower than the holdout error. It's not strictly speaking true because it's just with the validation error, it's just more variance. It could be much higher, it could be much lower. But probably if you do k-fold cross-validation, you overall get a better result. And then there's just 2 ways of how to averaging the folds. It's just a minor computational thing. If you think about you, one moment. Yeah, let's say you have just 2 folds. Yeah, it's a simple example. K equals 2. Oh no, sorry. No, you have 10 folds where you run this, and you get different results. You're not yet familiar with the meanings of this. We will talk about that in a future lecture. True positives, true negatives, false positives, and false negatives. But you know accuracy already. So there's only 2 instances in each fold. And based on these numbers, you can calculate the accuracy. You see here, half of the instances were classified correctly. Here, all instances were classified correctly. Half, all, and so on. And then you can either build the average of this, or you count through all the folds how many instances were correctly classified correctly as true positives, true negatives, false positives, and so on, and calculate accuracy on that. And for some metrics, it differs. I believe for accuracy, it's probably always the same. And for other metrics, you are going to learn like precision or recall. It might make a slight difference how you calculate the average, but the differences normally are minor. Still, for the exam, sometimes I have this in there. You should know how to calculate the different averages. It's a whole research field how to draw those folds. Do you just take random samples? Do you take stratified samples where you keep the ratio of different groups? How big should K be? This is just one of many papers. Like someone wrote 9 pages in small font about this with different experiments, like when to use which method. So if you're interested in more details, there's lots of work on this out there. Sometimes, or better said, typically, a simple holdout split or k-fold cross-validation is still not enough. If you want to do your experiments really good, you use a 3rd data split. That's the test set. Because there's a risk that you are still overfitting to the validation data. If you're unlucky and your validation data is just by chance not very representative for the future unseen data, you are overfitting your model to this validation data, because you basically choose the model that is best on the validation data. So this is an example. Let's say you do your iterations, and then you stop where the model is best here on your validation data. Okay, this chart is not really showing the importance of test data. Anyway, so this is how it would look like. You split your whole data into training, validation, and typically 10% maybe test data. And the test data set, you are not using for the training. You are not using it to continuously look at it. You train your model on your training data and validate it on your validation data. And once you believe you have the perfect model, you use this model one time on your test data and report this result. It's not for optimizing your model. It's only for reporting your result, assuming that the test data is the best possible guess of the performance on completely new, unseen data. It's really important to understand why this is important. To understand that once you continuously look at some data, like even the validation data set, you will have some bias in your model towards whatever this validation data looks like. And to get the best possible estimate of the true performance, you need a completely independent test data set that you have not used for training. So you take this data in the very beginning, before you do any pre-processing, before you remove any data, before you transform any data. Then you have your training and validation, and you can do whatever you want with this data. You can remove instances, you can transform data, you can fill in missing values. And then once you have the model, you apply it on this original test data. And the error very likely will be higher than on your validation error, be it k-fold or holdout. But it also very likely will be closer to the real error on the unseen data that no one knows yet than this data. Also, always keep in mind that the data you are working with often is just a small sample of all the data available in the company. And how to sample all this data, again, is a research field in itself. There's random sampling, there's stratified sampling. I mentioned that already. Okay. So when I say fitting a model, I mean to find the optimal model given your data points, to make the model fit your data. And when we talk about this, we also must talk about the bias-variance trade-off, again, relating to overfitting and underfitting. So if this would be your error curve on the training data, and this is the error curve on your validation data or on your test sample, then, and by the way, you will find some people call it train, validation, and test. You also occasionally will find the notation train, test, and validation. So if someone talks about test data and validation data, always be sure that you understand in which way they use that. Okay. So if a model is very simple, we say that it has a strong bias. And this is like you can, like, if a human is biased or is maybe applying stereotypes, they might make simple assumptions about the world. Well, they are biased in their minds. They think certain, or they generalize about certain groups or things in the world. And well, sometimes it's working. It's a very easy model to apply. If you think all people of this group are bad, that's a very simple worldview. And well, it serves okay to some people maybe, but it's not really ideal. So that would be in machine learning, the underfitting. It's a very simple model that is then also cheap to apply, quick to apply, but it's not delivering really the best possible results. And then you have people, then we have models and people with a high variance in their model. The higher the variance, the more in a tendency the data will overfit. Think of humans who are maybe overthinking when they want to make judgments about something or someone. It will be, so the model would be then fitted too well to some specific training data, but not for the real world data. So again, it's a too complex model. It's really like with humans. If your brain is making too simplistic assumptions about the world, or too complex assumptions where you think, oh, and here and here and here, both are not ideal. So you want to find the perfect bias variance trade-off here. Skip that. So I talk quite a lot about this topic because overfitting is one of the major problems. Well, I'm not sure if it's a major problem, but it is a real problem when you have production recommender system, machine learning systems. In previous years, before I came to Siegen, I gave this lecture and I demanded a little bit more than I do here from the students. So in the lab sessions and in homeworks, they had to participate in a competition on Kaggle. Kaggle is a web platform where people can where I uploaded a machine learning data set. Students could download part of the data set, use that for their training, upload the model or the predictions, made of their model, and then based on some unknown test data, unknown for the students, the model was evaluated. And so what you see then, there was a leaderboard that showed how good students perform on the test data and the validation data. So they had the validation data available, but not the test data. And so all these characters here are anonymous IDs of the students. And you see here the rank of the students. This is the rank on the test data. And this is the rank difference to the public validation data. So what this means is the student had a relatively good model on the validation data, but when used on the test data, it was 18 ranks worse than on the public data. And that is a very strong indication that he did overfitted his model. Other students, you know, like a difference of 1, even a difference of 4 or 2, that's to expect some difference between validation and test data. But if there's such a huge difference, or here even difference of 32, it means something is wrong. And in this case, most likely overfitting. We will not talk about too much about selecting algorithms. There's a lot of gut feeling involved. I showed that to you in one of the previous lectures already. This gives you a very rough guideline on when to choose which algorithm. And there's many charts like this, so we don't talk about that in detail. What I want to talk about is the algorithm selection problem that illustrates how difficult it is to choose the best and the right algorithm. So what you see here, it's an experiment that I did a few years ago in the field of recommendation systems. We applied 5 algorithms. You don't really need to know how they exactly work, but it's 5 different recommendation algorithms. And we evaluated them on 6 different news websites, German news websites. So that's the Kölner Stadtanzeiger, so the Cologne local newspaper, some sport website, some motor, a car website, some business website, a tech website, and a political news website. And what you see here is that the algorithms perform extremely different. So you see the precision, the higher precision, the better. And you see that on almost any website, a different algorithm is best and a different algorithm is worse. And the differences are massive between the different algorithms. So if you had your own news website, it would be really difficult to identify which algorithm to choose, unless you were to test them all. And there's not just 5 algorithms out there, there's many, many algorithms typically out there. And becomes even worse because even based on the time of the day, a different algorithm performed best. During the late afternoon hours, starting at 4 o'clock, here this white-blue algorithm is best. Here through the night, here it's midnight, so this is the time of the day. Down here, 2 o'clock in the morning and then 4 o'clock. But then during early morning hours and up to the afternoon, the yellow algorithm is best. Here, 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 and here. So what that would show to you is that ideally you apply 2 different algorithms. One algorithm in the evening and night, and another algorithm in the morning and during the day. And this is just one example, it's the time of the day. If you were to look at other factors like the device a person was using, like mobile device or desktop computer, gender, age groups, you would also find differences in how effective the algorithms are. That's a massive problem in recommender systems, also in machine learning, that really finding the optimal algorithm can be really difficult. Nowadays for certain things, LLMs are just clearly the best. So for image recognition, CNNs are still very good. But if some of you consider to go to a small or medium-sized company and maybe do your bachelor or master's thesis there, this happens often. The companies say, oh, I want this thing to do with machine learning. I want to predict something with machine learning. And I want a student to do this for me. What you will end up doing is, probably the entire time of your project, try out different algorithms. You will try out KNN. You will try, well, maybe not linear regression, but you will try out some other regression algorithms. You will try out different neural networks. You will try out random forests. You will try out XGBoost, which you will learn all about later in this lecture series, because no one really knows which algorithm is best for a normal machine learning problem. There's some indications, but you will. That's actually the reason why I typically don't supervise these projects with a company, because from a scientific point of view, there's nothing to gain. Yeah, only because you work in one company and then maybe you find out after 3 months, oh, this algorithm is the best. It's meaningless. In terms of scientific knowledge, it's meaningless because in a different company, a different algorithm will work best. It might be a good learning experience for you because then you will work a lot with machine learning libraries. That's a good practice maybe, but you could also do that at home. I mean, you can just sit down, take some data sets, try out different machine learning libraries, or go to the lab session. You also do that in the lab session. Yeah. So there is unfortunately not the egg-laying wool milk pig or something, eierlegende Wollmilchsau, in terms of algorithms and hyperparameters. And even when I just said for certain applications, maybe LLMs nowadays are just the best, they're not the best for everything. You cannot use a standard large language model to generate images. You can generate images with ChatGPT, but typically because ChatGPT then is sending your request to a different algorithm like Sora, which is generating the image. Any questions so far? Good. Then let's talk about pre-process. Yeah. Sorry. How do we know that the test data is like representative for the future data? It's a very good question. How do we know this? We don't. It's our best guess, our best chance. If your test data is big enough, like large enough, the chance is just very high that it will be good enough. But there's no guarantee. But it's still a better guess than using the validation data. Yeah. No, typically, at least with the data we are working, you use a random sample of your whole data set. And if your whole data set is large, let's say 1 million or more, and you use 10%, then this 100,000 sample for the test data will be a very good representation of the whole data set. The whole point is that if you have your validation data, let's say 20% of the data, you're still then optimizing your model for it, and therefore it will be slightly off. Typically, the differences between the test data and the validation data, it's not massive. It's not that you have an accuracy of 50% on your validation data and then 90% on your test data. It's typically maybe a few percentage points at maximum difference. So what can go wrong? If you have data, if you collect data, if you buy data, what can be all bad about the data? No? Yeah, it might not be representative for what? Like for the future, for the Yeah, for the general case, okay, yeah, yeah. Yeah, try to be a bit more specific or like even more low level, like really the data itself. What can be bad? Yeah. Okay, not enough. Yeah. Yeah. Incomplete in terms of, yeah, something might be missing, or the data is dirty, like in terms of noisy. You will definitely find that very often some data is missing. Why is that a problem? Like a massive problem? Sometimes, yeah. Yeah, it's going the right direction, but be more specific. There's like a really serious problem if data is missing. Yes. At least some algorithms, like linear regression, work with numbers, x1, x2, x3. That's your variables. So what do you do if x3 is not there? You cannot use null. Yeah? You cannot, in your database, you just store null. It's a null value. It's not existent. You cannot use this in linear regression. You cannot use null instead of x3 or x5. So what do you do then? We talk about that in much more detail, but yeah, for instance, remove the whole instance. You could do that. There's many other ways, but that's a serious issue. So far, we always had very simple examples with 2 or 3 features. What do you do if you have 100 features? Which features do you choose? Or even like in the examples before, do you use the student ID or not? I think we said in the beginning, yeah, it's not so important. I mean, it might have some meaning, because it's incremental and it tells you when the student enrolled, if the student is enrolled a long time ago or not. But this is just gut feeling. Yeah? There must be some better ways of choosing features, and there are better ways of choosing features. You might want to combine features into one feature to save space and memory, computing time, or just get more meaningful features. You might want to create new features to improve the performance. I mean, you can train your model to get better performance. You can increase the degree of freedom, take different algorithms. But if you are clever, maybe you can come up to create additional better data points. Sometimes you must transform features to make them suitable for your model. So you have a number or you have something, a string, and you must convert it. Either you must scale it or you must transform it to a completely different type of feature. Oh yeah, scaling. I think I mentioned that in one of the first lectures. In machine learning, we have the nice saying, garbage in, garbage out. If you have garbage data, you will get garbage result, even if you have a perfect model. If you have a garbage model, you would get garbage result, even if you have perfect data. So there's these two components, data and the model or the algorithm. If one of the two is bad, then your output will be bad. So let's start with feature selection. Which features to select? And I just mentioned it before. Things like student ID you might say, yeah, it's not so important, or the row ID is not important. No, it's probably also redundant with the student ID. But never ever trust what people call common sense or your gut feeling when it comes to machine learning. You cannot know which features have meaning and which features don't. So you must approach this a little bit more scientifically, a bit more like a computer scientist, structured. You must identify which features help you to make a good prediction. And a simple way, which is not so commonly used, but what you can do, also just when you start to explore your data, and it's always good to visualize your data. It's a heat map showing the correlation between the target and the variables, or between the variables to each other. So what do we have here? I need to. You have a heat map of all the features, and then showing the correlation is high or low. I just see here. Here, there's one feature with a very low correlation. Days employed. Not sure what that means. Anyway, so you can calculate correlation either between the features themselves or between the features and the target. And you want to pick those features that have a high correlation with the target. I think that's quite plausible. If there's a high correlation between study time and salary, then that's a good predictor. And very likely machine learning, linear regression, or whatever will be able to see the linear. I mean, if there's a high correlation, that kind of means there's a linear relationship or a model that can model this. And ideally, you want low correlation between the variables themselves, because then they are redundant. If you have two variables, let's say study time and average marks, and there would be a perfect correlation, 1, then you don't need both variables. They exactly express the same thing if they have a high correlation of 1. There's different ways of calculating correlation. Pearson correlation is typically the most common ones, but there's many other correlation metrics as well. Now, the problem is, if you have a heat map like this, it's still difficult to then really make a decision which features to choose. I mean, you can do it, but it still requires a lot of manual work. So a more common method is a wrapper method. With a wrapper method, you just try out different options. It's the hill climbing approach. It's a greedy search approach. There's variations, forward feature selection and backward feature elimination. So with this one, you start with 0 features and you find the single best feature. So you basically train a separate model for each of your features and look which of these features is best. Then you keep this feature. And then you take the next best feature. So you take this one best feature and build again many models with this one first feature and another feature, and the first feature and some other feature, and the first feature and one more feature. And you look which of these models that has now 2 features, or that is trained on 2 features, performs best. And then you keep those 2 best features, the model that is best and trained on 2 features, and you add the third feature, and you look which of the third features is best. So that would look like this. And then you would, I mean, I don't know why this goes up and down again, should not really happen. Typically, you would then use those 13 or whatever features that are best. You can also do the exact opposite. You just start with all features and remove the worst feature. And then you remove the second worst feature until the performance doesn't decrease anymore. What's the problem here? No? Yeah, it's a lot of work. Because ideally, then you should also use cross-fold validation to have a reliant, to have a good result. And if you have 100 features and this is like exponential kind of. You have a very high computational load, quite expensive. I'm giving you just a rough overview of all these methods. Right? For each of these methods, you will find different variations in scikit-learn, lots of research on that. So this is giving you just a rough guideline on which feature selection method you might want to use. Yeah, I will not ask this in the exam. And just if you search for machine learning feature selection, you will find almost 100,000 research articles that deal with this topic. So it's crazy. Just about choosing the features. There's almost 100,000 documents about this topic since 2017. Another important aspect, data cleaning. So I'm talking a lot there. You will have to learn many, many things. The best is really at home, take these slides or go to the lab session and try out all these things. You will, all of this is very easy to do in the software libraries. Scikit-learn has just a function for feature selection. Scikit-learn has a function for data cleaning. So you can play around with this, maybe have a look at a few data sets at home to see what the effect is, or just to see how it works. Data cleaning is about, among others, dealing with noise. Noise is incorrect, false information, and it can affect both the features and the targets. There can be stochastic noise that is random. Yeah, for instance, if you measure your body weight a couple of times during the day, it's always a little bit different. There can be human error for various reasons, just by accident, or because humans want to save time. So instead of measuring the temperature of a patient, the nurse, instead of measuring the temperature of a patient in the morning and in the afternoon, the nurse might decide in the afternoon that the nurse just copies the value from the morning because it will save a few minutes of time. Systematic noise drags all measurements in the same direction, like a miscalibrated thermometer. Or a really annoying thing if you work in web online shops or some other online platforms, you somehow must deal with web crawlers, with bots, like from search engines or AI engines that crawl the web to index your content, to use it for AI training whatsoever. They are not humans, but they increase, I mean, depending on what exactly you want to do. One example that I experienced was I was developing a recommender system. We displayed recommendations on a website, and we were measuring how many people were clicking on the recommendations. Now, the bots, the search engine bots from Google, they were just following all links on a website. So they were basically clicking every recommendation we gave. And in the beginning, we thought, oh, amazing, there are some people who follow all our recommendations, but it's just a robot that is crawling the web. So you must, and we just discovered that a few weeks or even months after we started data collection. So we basically lost all the data because it was worthless due to all the robots, and that we were not able to identify that in retro perspective. Just one example. Yeah? So you need to think about that already when you start collecting your data. Now, the solution is very easy to say, delete or correct the data if possible. It's a big if. The first step is identify the noisy data. That's actually the problem. That's one of my favorite examples that I always like to show in different lectures. There's an experiment. What was it about? Okay, I don't know what the experiment exactly was about, but you probably know that people in medicine and biology often do experiments with mice. And they give some medication to them or measure something like the stress hormones of a mice or whatever. And in this experiment, researchers, I believe in different locations, in different labs, got various results, very different results. And in the beginning, they could not explain why is that. They had very similar settings in the two laboratories, the same animals, like the same race of mice, and the same medication, and so on, but the results were very different. And then after some time, they found out that the lab mouse, what's the plural of mouse? Is it mice? Yeah. The mice, they react differently to different genders. They react differently to men compared to women. So based on the gender, the mice had more or less stress hormones. Yeah, that is noise in your data. But imagine how difficult that is to find that out. I mean, your first guess is probably something must be different in the laboratories, the environment. Maybe the medication is different. Maybe the air is different. Maybe the food is different. Yeah, how long it probably will take to get this idea and then to show that this was really the reason. So that's really hard to detect things like this. Suppose this is completely made up data, but suppose you have recorded the temperature, not you, but someone, you have a data set which contains the temperature over the past more than 100 years and how the temperature develops over time. And then you see this data point. Is this an outlier or noise or both? Outlier? Why? Yeah, so I would say it's very likely an outlier. It depends on how you define an outlier, and we talk about that also in a few slides. What's exactly, I mean, it's quite far from the other points, right? So you probably naturally would say, yeah, that's an outlier. But what if this point was here? Was that an outlier? What if the point was here? Or look at this point. Is this an outlier? You must come up, as a computer scientist, you must come up with a numeric value to say, okay, that's an outlier, that is not an outlier, and then decide what to do with the outliers. Is this noise? Yeah. There was in 1994. Okay, so I made this data completely up. Yeah, so if there was some special event in North America at this time, then this is a very interesting coincidence. And the right answer here is you don't know if this is noise. Noise is incorrect data. So, yeah, like if you see, if this is all the data you have, and then you see this, a good thing to do is what you did, maybe look it up. Like, was there some very strange weather phenomena in this year? Or are there other records showing that temperature really was like this? Or maybe you can ask your grandparents or your parents if they remember the winter, or no, it's not winter. Anyway, if they remember this year, if it was very cold, then you might know it wasn't, like, if it's incorrect or not. Just looking at the data itself, having a data set without any additional information, you cannot say if something is noise. Now, that's always external. I mean, the data set typically does not contain the information the thermometer was miscalibrated or the nurse was lazy and just copied the entries. That's something external, not in the data set, that you would have to research and find out. So if all you have is this chart, you don't know if this is noise or not. How about here? The same. I mean, and this is now very clearly an outlier. and very likely an incorrect data point, but again, you cannot know 100% sure. But maybe it also doesn't matter if this is noise or an outlier. You probably want to remove this data point, because if you think about fitting a model, you probably want the model to be here, like this straight dotted line. But if you were to build a linear model, you probably would end up with, I don't know, with something, yeah, I don't know, with something that is not ideal. Outliers can have a very strong impact how your model looks like. So this is real data. If you fit a linear model on the original data, it looks like this. Yeah, quite steep. If you remove those outliers here, you oh, one moment. Sorry for those joining online. Oh. So if you remove those data points, you end up with this model. So it looks completely different. And again, you cannot say this is better than the other. These are some real experiments, what the impact is of outlier removal. You see two different algorithms. Linear regression and random forest and different outlier removal methods. So if no outliers are removed, you have a root mean square error of 0.93. And then there's different methods, which I explain to you in a minute. And you see that RMSE goes down a lot, like this is basically roughly half of this. And here the error is even lower. But you see also that among the different methods, there's a big difference. If you look now at random forest, a different machine learning algorithm, you see that no outlier removal has the best performance, or basically the same as this and this transformation. So there's no right answer what exactly to do with outliers and when to do what. It's like, again, gut feeling and trying out a lot. Another problem is that outlier detection normally focuses on one single attribute, but sometimes it might be that there's dependencies between the different variables. And in theory, it would, or actually in practice, it would make more sense to look at maybe two attributes together. But yeah, that's just typically computational, not possible. We have an exercise now, and I think we also use the time to have a short break. So during the break, you can talk with each other, you can read this. First of all, read this first, and then on the next slide, I give you a news article that you can read. Yeah, so here just again in brief the questions. Please read this article and think especially about the third question. I would say we meet at 2 o'clock again, so 10 minutes. read this, get a coffee. Okay, let's continue and let's do the Mentimeter. Also, those who are online, please go to this website, type in the code, and tell me, what do you think? How well would the data work? Okay, there are 35 students in the Mentimeter, but 16 submitted a vote. Anyway, let's see what those 16 think. Okay, very different opinions between not at all and good. What's this one? Undefined. Yeah. What is it? Okay. So let's go back to the slide. Who thinks this would work reasonably well? And why?
I don't know.
Okay. Okay, good. Who thinks it might not work very well or not at all? Okay. So if I told you the data would be completely useless for machine learning in this context, and one moment, so think about this for 1 minute. The right answer is it's completely useless. Why? Maybe someone who's not always someone new, who never says anything and wants to express their belief.
Don't think very relevant that because it's York City from before. That's almost absolutely.
Yeah, let's ignore that. Let's assume this is all in the same time. No, but there's a very simple reason why this data is completely useless. Think about and it's about the representativeness of the data that you have. And it's a very good example that many of you thought, at least initially, might work quite reasonably well. Because this is a real world example. It's a newspaper article that is published in, what was it? New York Times, I think. Yeah, New York Times. It's a very reputable journal. This whole article is crap entirely because all the conclusions being drawn here are false. Think about again, what kind of cats are being brought to the hospital? Yeah. Exactly. Those who survived, or at least where the owners had some hope it would survive. Those cats falling from the 10th floor and being completely mashed potatoes after arriving at the floor are not being brought to the hospital anymore. So you have a very strong selection bias in here. Those cats who are being brought to the hospital very likely are a small subset of all the cats falling from the windows, of which, I mean, who knows, but possibly the vast majority dies if they fall from the 10th floor. So you cannot use this subsample of data as a representative sample of the whole population. You cannot train a machine learning model based on this and then expect that it would work well for all cats falling down the windows. And the reason, I'm sure, why you were not thinking of this and why also this was published in the New York Times is it looks so scientifically. It's, I think it's a doctor, right, who collected the data, and you have so much detail about the average floor it's falling about, and yeah, whatever. I mean, here look at all the numbers, and then you have even explanation why maybe cats tend to survive all these falls, like the flying squirrel, or like their tail is like a helicopter. I forgot. Yeah, like a flying squirrel, increasing the air resistance. So we have a kind of plausible explanation, and you're being blinded by this instead of critically challenging the whole validity of the data. And this is something that happens very easily. It should not happen to a journalist from the New York Times, but it definitely happens to many people working in a company because you're so focused on what you have that you forget to look at the bigger picture. And it's difficult to learn how to do that. It's just practice, I think, and just a general critical mindset. So also one reason I show this to you is because it's a real world example and it's a newspaper. And yeah, it's very old, but you see very similar examples nowadays in the newspapers. Many journalists have very poor education in statistics, and in any way, they have a very poor education. So you should be always very critical when reading any news article from any outlet. Yeah. Yeah, of course. If you change the task, then the data might be suitable. If you change the task to from those cats arriving at the hospital, how many or which cats survive? Well, yeah, that probably would be a valid machine learning task then. Good. Let's get back to, well, to the pure machine learning part. When talking about machine learning pipelines and evaluating machine learning, what is important are distributions. And I'm not sure if you had this in prior math lectures or maybe even in high school, normal distributions like this. So if we were to measure the IQ of all the people here or at the whole university, then the average would be roughly, at least in the whole population, would be roughly around 100, the average IQ. And we would have a distribution as shown here by this. So there would be roughly around 68% actually with an IQ, so 68% of all people would have an IQ between 85 and 115. And then like a very small percentage would have an IQ higher, 145 or below 55. This is called a normal distribution or the bell curve. Maybe you have seen that. And then the distributions. And it's surprising how often you see normal distributions in nature. We could measure your IQ, we could measure your body height, your body weight, we could measure your income. Very likely, almost whatever we measure, it would follow a distribution like this. If you repeat experiments many times, you would also end up with a distribution like this. Thinking back of k-fold cross-validation, where you had those 5 different points, you would end, and if you would do this like 100 times maybe, you would end up with a distribution like this. So you would have the average of those 100 points, and then most of your points, and you would have some result. Let's say the average of your 100 folds would be 5.8. Now the average would be not 0, but 5.8. Then 68% of your 100 measurements would be here in a certain interval called the standard deviation. And a few measurements would be very far off in this direction, and a few measurements would be very far off in the other direction. So among all of, well, I mean, the mean is obvious how to calculate that, it's the average. And the standard deviation is calculated based on this formula. So it's the difference between the current value you're looking at and the average value, and you square that difference, sum it all up, and take the square root. And then you have the variance, which is not, I mean, you need the variance to calculate that, but it's otherwise not so important now. And you have the standard error of the mean, which is just the standard deviation divided by the square root of the number of observations. We talk about the standard error of the mean later, I believe. The distributions can be more skewed or less skewed, depending on the standard deviation or the variance. And while the normal distribution is very common, there's also many other distributions in nature, in computer science. So one other really common one is, where is it? It's not here what I'm looking for, it's on the next slide. This one, a typical long tail distribution. You also find that often. So if you were to look at the size of cities in the world, or even with one country, you'll find a few one being extremely large. So a few one here being very large, and then many that are quite small. So it's a long tail. From here, it goes down like this, and then here you have a long tail, much longer. Right? It would go like here. If you order all the cities in the world, for instance. You have that also in e-commerce, for instance. If you order your products based on whatever, based on the price per item or based on the revenue items generate as part of your overall revenue, you will find that there's a few extremely expensive items and many low price items. You will find that there's you will find that there's a few items that contribute a very large percentage to your overall revenue. and then many, many, many items that are being bought only very rarely and hence only contribute very little to your overall revenue. Same with everything. You know, the views of movies. Of all those views on Netflix, probably there's like 10 movies that generate 80% of the views, something like this. So coming back to the evaluation of machine learning, this one I showed to you before. It's showing to you, is a legend here? No. So that's the training error, very likely. The blue one is the training error, and the red one is the validation error. You see all these light lines. So there were many repetitions of experiments. So one time it was like here, this line, and another time you had this red line. So there's dozens or hundreds of experiments, and the bold line is showing the average of all the thin, light red lines, and the same for the blue lines. So if we look now at this point, where is here a normal distribution? Mm-hmm. Mm-hmm. Yeah, it's difficult to explain. Yeah. So I assume you meant the right thing. So each point on this line would be the mean of the normal distribution. And then you have many experiments just being around here, the result here, 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 here. And you have very few experiments that are here. So just to illustrate that. So what that also means is if you run your experiment a single time, there's a good chance it's close to the real. So let's assume that this is the real value. If you just do your experiment a single time, there's a good chance that you end up on a line that is also close here or here. There's a 68% chance that you end up somewhere between here and here. But there's still like a 10% chance that you end up somewhere here, and hence are quite far off. We also can use normal distributions to choose what is an outlier. In the same way, we could choose that to say which IQ is an outlier. What is a normal IQ? The average is 100. That's obviously normal by definition. The average is ordinary, it's normal. What about 150? Don't get like confused by the colors. That's from before, that this would be about 68% of the population within here. So what's an outlier for an IQ? 115, 130, 145. 150 or 160. So, but that's just your opinion, right? Yeah. So same on the other side. That's true. Like it's symmetric, but there's no natural law telling you this IQ is an outlier. It's just a definition. It's just a way of calculating this. And just one way of many is the Z-score method to identify outliers. So what you would say is, if someone has an IQ here, it's moderately unusual. I mean, like this is very common. 68% of the population have that. This is another 12%, I believe, 12.5. So that's still not so uncommon. This is quite uncommon, and this here is very uncommon. So some people suggest that if the Z-score is larger than 3, that should be considered an outlier. And here the Z-score is actually calculated as X, so the point in question minus the average divided by the standard deviation. And we also talk about confidence levels. So if Z equals 2.58, that would be then here, 99% of your population would be between here and here. So if you really have a Z-score of 3, that is probably, is it in my notes? No, that would probably be 99.9% or more. So that would be actually a very extreme outlier, I would argue. There's a different method to detect outliers. So all of this is relevant for the exam. There's a good chance that this or this will come in the exam. The outlier, the box plot method. Do you know what a box plot is? Have you ever created a box plot yourself? Yeah, in which lectures, or not in a lecture somewhere else? Oh, okay, in the seminar. Yeah. I like box plots. It's like the most simple way of representing something is a bar chart, right, or a line chart. And the box plot gives you a good understanding of the distribution. So for now, assume, one moment, assume you have those measurements of whatever, or your targets in your data set, 13 observations. Then the box plot is telling you the median value, and you can do it with the mean as well, but often the median is used. It's easier to identify. So the median is 8. If you were to sort this list, like decreasing or increasingly, and then the value in the middle would be the 8. And you know the maximum value is here and the minimum value is here. That being said, like this outer whisker, this and this, it's often not used to show the minimum and maximum, but rather Q4 or Q0, which I get to in a second. So it shows to you that 50% of the data is here and 50% is here, and 25% of the data is here. Or in other words, 50% of your data is between here and here. So it gives you a good idea of how far the data spreads, about the variance and the distribution in general. And to identify outliers with the box plot, what you do first is you identify all the medians or the interquartile ranges. So you find the real median and then the sub-median. The sub-median is just the median between here and here. If there is no value, you take the average of the nearest neighbors. So here you have 8, 7, 7, 6, 4, 4, 2. And it's an even number of elements, 1, 2, 3, 4, 5, 6, or 7. Is that correct then? I'm thinking, should the median be 6? I have to double check that. Anyway, you calculate the median here and here, whatever it is. For now, we assume it is 13.5 and 5. And then you calculate the interquartile range. The interquartile range is just by subtracting the two medians from each other. So here it's Q3 minus Q1. Q3 is here, and Q1 is here. And you calculate here the upper limit. Sorry, this is the lower limit and the upper limit by taking Q3 plus 1.5 multiplied by what you've just calculated here, the interquartile range. And the lower limit exactly the same, only that you subtract the data. And then by definition, we have here the lower, here the lower limit, and here's the upper limit, here, this line. And then by definition, again, it's not a natural law, it's just, I don't know who decided that, someone decided that someday, you would consider everything here an outlier and everything here to be an outlier. And there's many variations. Actually, this one is probably the most common one, where outliers are plotted as like dots beyond the lower and upper fence or whiskers. And that's a mathematical method of determining an outlier. Before I ask you, is this an outlier? And then you said, oh yeah, probably, yeah. And sometimes it's kind of obvious if you just look at it visually, but you also must do this for millions of data points, possibly. So you cannot always look at the data and say, oh yeah, this looks like an outlier. You need an easy to calculate method to do this. And there's many methods more. Like you saw on one of the slides, there's a log transformation works, but that's actually not an outlier detection. It's more a transformation method. Anyway, so there's many methods more. We will not go into detail. If you work with scikit-learn, you have different outlier detection methods. And then the question, once you know something is an outlier, the question is, what do you do with it? And I think in the very beginning, someone of you said already, when data is missing, if one piece of information is missing, and we can do the same with an outlier, you can just remove it, like the whole instance, for instance. Or you just don't do anything. You saw in one of the previous slides that sometimes, in that case with random forest, I believe, not removing outliers was almost the best performance, or almost as good as doing something else. Another simple way of dealing with outliers is the Rinse-Arise method. So you decide on a top and bottom threshold, for instance, the top 5% of data, and you just Rinse-Arise it. Rinse-Arise means you replace the data with the next valid value. So if you have an 80% Rinse-Arization, it means on the beginning and the end, you take the 10% of the values here, like 0.1 and 1, or 99, 125, and replace it with the last valid value. So replace that with 44. Here it's 44. Here replace those two values with the 12. It sometimes works well, and sometimes it doesn't. Or you can transform your data, like all your data, not just the apparent outliers, but if you transform data by taking the square root or the log, or normalize or standardize them, you will just have less outliers. Now think about taking the square root or the log of something. It will make very large values quite small and will affect small values less strong. Here we have missing values. Either like here's a dot in here, or no data at all. And you must deal with this as well. And we talked already about the problem that missing data can cause, that with some algorithms, you just cannot use the whole instance, then the whole data point, because linear regression, for instance, needs a value for each variable. Let's talk about why data can be missing. There's multiple reasons. One reason is data can be missing completely at random, which very rarely occurs. And so I think I took this example from a book that said an example of missing completely at random are some surveys being lost in the mail. But even that, I would, so if you send out a survey, a questionnaire to people by mail, sometimes the mail gets lost, either when you are sending the mail or when the recipient sends back the survey. And I would argue even that is not entirely random. I would argue that probably in some areas of Germany or even in the world, it's more likely that mail gets lost than in other areas. I would just hypothesize, I don't know if it's true, but I would hypothesize that maybe in a big city, maybe especially in a poorer area, it's more likely that mail gets lost than in a village, for instance. Because, you know, it happens once in a while, you maybe see that in the news, that a postman is not delivering the mail and keeping it all at home because the postman doesn't want to work, something like this. And I think this would not happen in a village, because in a village, immediately someone would recognize that this postman is not going to deliver the mail and staying at home. In a big city, this is less likely. Or in a very poor area, it's probably more likely that mail gets stolen. It's just hypothetically, yeah, but I think it's not entirely random. So it really rarely occurs that something is entirely at random missing. So much more likely is that the reason that data is missing is conditionally at random. That means the probability of the missing value relates to some other variable. For instance, older people tend to specify their IQ less often in a survey if they know it. So if you send out a survey to people and you ask them, what's your IQ? And then you get the surveys back, and some people will not specify their IQ. There's a tendency that these people are older than those people who specify their IQ. Yeah, I mean, first of all, the people need to know their IQ. I don't know who here knows their IQ. Not too many. So I'm not sure if you don't want to tell me, because you're not really old, right? But still, maybe you're reluctant to tell me. Or if you just don't know. I also don't know my IQ. But even those who know are more reluctant to tell you if they are a bit older. So one variable is related, the missing variable is related to another variable, which you can use then as information. If this piece of information is missing, you can possibly use that information to make assumptions about the age or whatever your target is. And then sometimes the missing variable is related directly to itself. Probably not surprisingly, people with a low IQ, even if they know their IQ, are less likely to tell you what their IQ is, because it's embarrassing if you have an IQ of just 50. And people who have a very, very high IQ are probably more likely to tell you because they are proud of it. Unless it's too high, then they maybe feel embarrassed and to show off. So is missing data bad? Yes, absolutely. So you must impute your missing values. Impute is just a very nice name of saying you must somehow deal and fill your missing values. And what you indeed can do is just delete the entire instance. If there's just a small number of data points where you have missing values and you have a large data set, just delete the data. Like if it's like smaller than 5%, for instance. Or you can encode it as missing. You can use maybe a -1 if all the other values are possible. Or you can add an extra column like data is missing and then put some other number in there. Or you replace the missing value with some estimate. The average of all the other values or the median. You can maybe interpolate the data based on what exactly is missing, or you can even use machine learning to make a prediction for missing values. Each of these approaches has potential problems. It's a very strong assumption that a missing value is best replaced by the average. And after that, you have possibly a lot of people with this particular average value, or if you encode it as a -1, like if you have numeric values, let's say ranging from 1 to 100, and then you add a -1 to imply it's a missing value, then the model will consider this missing value -1 to be very close to a 1 or to a 2 or a 3, much closer, for instance, in the vector space than 100. It's difficult to say. Just show you a few ways of visualizations. This is a bar chart. I'm sure you're aware of that. That's a heat map, a correlation heat map. Here's a decision. I think I can, one moment. Yeah, I think I can, I will delete that right away. It's not, I mean, you know those things. It's a decision diagram, how to deal with missing data. Again, it's not always exact science what to do, but it gives you some good rule of thumb. We will not go through that. I will not ask you that in the exam. And like always, if you ask what's the best method, there is not the one best method. That's the reason why I show them all to you. Here you see different data sets, the iris data set and the E. coli data set. You see different algorithms for imputation. So I'm just taking the mean value, taking K and N, so machine learning, and this is some other machine learning algorithms. And you see, and then this is the metric, how to measure performance, RMSE, so root mean square error, and some other metrics. And here's the percent of missing data. And you see, well, what do you see? Here, the blue algorithm is best. Here, I'm not sure. Also, the blue is maybe as good as this violet algorithm. Here, the blue algorithm is second best. So there's not the one method that is always perfect. So even, I mean, what's this one? FKM. I don't even know what FKM stands for. That performs quite poorly here. I don't know why. Yeah. Yes, you're absolutely right. So yes, well spotted. Lower is better. I mean, no, it is right that it's increasing because it's more missing data. So the more missing data, the worse the performance. But yes, not the blue algorithm is best, but at the bottom, the lower RMSE, the better. So yeah, you get the point. The green algorithm here is best. Well spotted. And again, there's lots of work on missing data. If you want to read more, that's just one of thousands of research papers again. Then there's inconsistent data. And that's a really, like if you work in a company, this is something you will stumble up on if the company is, let's say, a few years or a few decades old. At some point in time, or if different programs write their data to the database, you will have different descriptions for the same thing. Just as an example, for gender, you will have sometimes just a letter, sometimes the whole word, sometimes the number. Yeah, just very annoying because to find that out, like again, these are all simple examples. I just show here 4 or 5 variables to you. But if you have a large data set with thousands of variables, and sometimes things that you don't know, you are a computer scientist, and then you work in a biological pharma company, and they give you a large data set, and they have some weird names of their variables that you have never heard of. So you cannot decide or see if there's 2 things describing the same entity. So to find this out, very difficult, often very annoying. But this could really strongly decrease your performance because then your machine learning model will consider this as 3 different things, although eventually it's all the same. Or near duplicates, I still have to create some slide for that, but what's a near duplicate? Do you have any idea? I mean, a duplicate, of course, is a problem if you just have multiple exact copies of the same data, but that's easy to identify, right? I mean, just, yeah, that's 1 line or 2 lines of code. What's a near duplicate?
For example, and one person sends in the form 10 times over the course of multiple years, but only one.
Yeah, I mean, I don't know if anyone would send in 10 times the same survey, but maybe they sent twice. Well, maybe they got the survey even 2 times. So it's one person, and only one person should submit one survey. Or another problem, like from when I was working and developing a recommender system, like I mentioned, we delivered recommendations to a website. The recommendations were displayed on the website. And in the very beginning, so we were logging if a user clicked a recommendation, but we just forgot that it could happen user clicks the recommendation twice, or some people like a double click, because they used that from their Windows Explorer. And then there's 2 clicks. And in the very beginning, we just recorded both clicks. And because the timestamp was slightly different by a millisecond or by 1 second, we had 2 entries in the database that at least were slightly different, namely the timestamp was different. Again, I mean, that is easy to fix, but at least if you have something like a user ID. If you don't have a user ID, then this is actually difficult to fix. And there's hundreds of things like this that can happen. Feature engineering. That's also a whole research discipline in itself. What to do with features. If we have our cost function, if we have our linear model here, can you put a string like this in here? If you want, so x, j in this case, let's say it's gender, and now we need to find a weight that is weighting the gender. Can we put a string male in here? Huh? Yeah, we need a number. Yes. It would work. The question is how well it would work, but at least we could calculate something. So it would work definitely much better than having a string. A string just doesn't work at all. It's not possible. You cannot put a string here and weight the string. You need to do something with it, and you somehow must transform it to a number. If it's 1 and 0, we will discuss, but it must be a number. Here we need a number. It's the only thing working in linear regression. A numeric value that we can put some weight in front of it. Unless we say we just ignore this feature, but yeah. Often you have features that have strings. City names. What do you do with city names? There's just a string behind that. So let's consider 2 options. You could do something like this. So let's consider 3 genders. 1, 2, 3. And you could replace this with numbers. 1, 2, 3. Male is 1, female is 2, and diverse is 3. Or you could also encode it like this. Just binary. What do you think is best? Yeah, that's a good point. If you replace one variable like a string with a numeric value, 1, 2, 3, 4, 5, then you automatically introduce some weight among those variables. Yeah? Then diverse would be 3 times as high as male. And female would be 2 times as high as male. And and female would be closer to male than diverse would be to male. So probably it would still work okay, but maybe not perfectly. So we ignore this. What you very often do, not always, again, not always, we talk about that also. What you often do is you convert your features into binary variables like this, like on this slide. And you can ignore one feature. Why? Exactly. So it's redundant information. If this is both 0, then it's clear that this must be 1. Or I mean, the machine learning model is not aware of this then, but it doesn't matter. You can, I mean, there's 3 options. This is 1, or this is 1, or this is 1, basically. So if both is 0, that is still containing the same information as if this is a 1. Saves space and works better. And it even works much better. It's called the dummy variable trap. So in general, this is called a dummy variable because it's like an additional dummy variable. And in linear regression, it even can cause serious problems if you encode it like all of that. I think maybe we talk about that some other time, why that is. But for other algorithms, like in SVM, we will not talk about that algorithm, support vector machines, you use all variables. Yeah, I mean, you can do this. This is good homework. Find out why it is. It's not part of the exam, but it's a good practice. Now, and sometimes, now, new topic, some variables have no immediate meaning. You see the variable, and it's kind of meaningless to you and possibly also to the machine learning algorithm. Something like this, a ticket number, or, but by the way, this data set, it's the Titanic data set. It tells you which passenger survived and like where they were located. Like here, the cabin, and was it first class, second class, how much did they pay, the gender, and here if they survived, the age. So in this case, the cabin number is kind of meaningless. If you would transform that to an information like this was in the bottom of the boat, or it was in the higher deck, or it was in the front or in the back, that could make it much more useful for a machine learning model to understand the meaning and then maybe make a prediction if a passenger survived or not. Or if you have numeric values like GPS coordinates, longitude and latitude, that also is relatively difficult to understand for a machine learning model. A machine learning model first would have to understand how this whole coordinate system works. It's quite complex, and it consists of 2 variables. So just looking at one variable is quite meaningless. You always need to look at both. So it could help a machine learning model a lot if you transform that into, for instance, the country or the city or whatever you want to use this for. And once you did this, you would use dummy variables again. So encode the country and the city. Sometimes this helps massively to get better performance. Another thing, scaling features. For many algorithms, like linear regression, variables with a larger scale have a stronger impact if you use something like, or in k-nearest neighbors, if you use Euclidean distance. If you look at this, I mean, the scale and the physical distance, again, is not the same, but you would probably cluster it like this. if you have then one outlier with a much higher salary, it would look like this. So what you need to do is, or what often is useful to do, is to scale your features, make them to the same scale, especially for algorithms like KNN and also linear regression. Some methods, but they don't really scale to the same units then. Just take square root or log, or sometimes to square the values. That is just making the values more similar. But what is more common is min-max normalization or Z-core standardization. Those are two things you should know for the exam. So the min-max normalization or rescaling is scaling to a value between 0 and 1. So among all your data, then the value that is smallest will be scaled to 0, and the value that is largest will be scaled to a 1. And the way you do this is you take the value in question x, subtract the minimum value of all the x values, and divide it by x max minus x min. So if you have the largest value, this will give you a 1, and if you have the smallest value, it will give you a 0. Yeah, and then you have the Z-core normalization related to what we just talked before with the normal distributions. It's assumed that it's a normal distribution, a Gaussian distribution, and your data is scaled in a way that your mean is 0 and your standard deviation is 1. So most of your values after that will be between minus 1.5 and 1.5, and pretty much definitely between around minus 3 and 3. This is work used often for these type of algorithms. And this is how you do it. You take the value in question, subtract the average value, and divide it by the standard deviation. And that is then giving you the values. So here's an example. If you have here 11 persons, you have their age and their income. You have here min, max, mean, and standard deviation. And this is the results for the normalized min, max. So between 0 and 1. It's coincidence that 0 is here in the top and 1 is at the bottom. That's just coincidence. And here, yeah, values between smaller than minus 3 and plus 3. So here, like 2.35 minus 1.60. Yeah, I think actually we stop here because my voice needs a break. And we will just continue not next week. So next week is no lecture. I'm not sure when's our next lecture. 2 weeks? 3 weeks? Anyway, next lecture, we will continue here whenever it is. Thank you very much.